Okay, so we're getting ready for an assessment here on the first 5 lessons of Unit 2, Topic 3, okay, on our systems of equations and inequalities. So we have Tommy and Kate going to make and sell some baked goods here. They're going to make pies and they're going to make cakes. Right? So we have some information about how long it takes to make each one and how long they have total to work. And then we have information about revenue, which revenue, just think of it as money. It's technically all the money that you bring in before you subtract your expenses. So it's like income, right? So they want to make at least 108, and they're going to sell pies for 12 and cakes for 9. So our first step is to define variables. Now, that's what we've been calling let statements. It does not mean write a definition for the word variable. So define our variables. Well, what are our 2 unknowns? Okay, we know how long it takes to make a pie. We know how long it takes to make a cake. We know how much a pie costs and how much a cake costs. What we don't know is how many of each one we're going to try to make. So those are our variables, and it doesn't matter which one you use, which letters you use and which one you call pies and which one you call cakes. But I don't know number of pies and I don't know number of cakes. That's what is still to be determined. What are the constraints? Now remember, the constraints are like our limits for the problem. And we don't need to get into, be specific and recopy everything from those tables. All we need to do for that question is just say that we have 2 constraints. They are about time and revenue. Okay? You do not need to be specific and start listing the hours and the prices. All right, number 3, now it gets real. Now we're going to write our inequalities. And remember, we've already said that pies were X and cakes were Y. We'll need to remember that and be consistent. So we write one inequality for each constraint. So the inequality regarding time. Well, a pie takes 2 hours, and I'm going to make X pies. So that's 2X is the time I spend on pies. I'm going to spend 3 hours on every cake and make Y of those. So I'm going to add 3Y. And then no more than 24 hours total for all my baking. No more than is not more than 24. I can use 24 hours or less. So less than or equal to 24. For the revenue constraint, we want to make at least 108. So that means at the very lowest 108. We would certainly be happy with more. We're going to sell pies for $12. Well, I'm baking X pies. I'm going to hope to sell all of them, so I will make $12 for every one of those X pies. And then my Y cakes will each sell for $9 each. So I'm going to add on $9 for every cake. And how do I indicate I want at least 108? That means I want greater or exactly $108. Okay. So we need to graph those 2 inequalities. Let's start by labeling that we said X would be pies and Y would be cakes. And this graph is for our fundraiser. So, scale. Well, let's think about how we're going to graph this. Since these are both in standard form, I would think you would probably want to put the lines on the graph using the intercepts. So let's do that. And we know we won't have to go any higher or lower than those intercepts. So in this purple one, our x-intercept is when we substitute 0 for y. So this term 3 times 0 is just gone. And we have 2x is 24. Well, divide 24 by 2, our x-intercept is 12. Our y-intercept is when I substitute 0 for x, and this term is gone. So 24 divided by 3 is 8. With this revenue inequality, same procedure. For x-intercept, I ignore the y term. So 108 divided by 12 is 9. For the y-intercept, I ignore the x term. So 108 divided by 9 is 12. So it looks like if I can number to 12 on both the x and y axis, I'll make it. So I have 2, 4, 6, 8, 10. Yes, I can count by ones. So here's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8. All right, so since I already have those intercepts, excuse me, it would certainly make sense to go ahead and put the graphs or the lines on there now, and then all we have to do is figure out the shading. So for this purple, this time line, the x-intercept is 12, and the y-intercept is 8. Since there is an or equal to, that will result in a solid line. And again, since pies and cakes can't be negative, like many of our other scenario problems, we do not extend that line beyond the x and y axes. There's no reason to graph any negative values. Now, as far as shading that one, since I used the intercepts and I did not solve for y, I'm going to go ahead and just do a test point. So I can use 0, 0 as long as it's not on the line, and in this case it is not. So when I test 0, 0, in here that's 2 times 0 plus 3 times 0 less than or equal to 24. 0 and 0, so 0 less than or equal to 24. That is true. That means the point 0, 0 works, and it must be shaded. So therefore, I'm going to shade everything below this purple line. All right, for the orange line, the one for revenue, x-intercept is 9, y-intercept is 12, also a solid line because of this greater than or equal. So solid line. Also no negatives because x and y still represent pies and cakes. And I will need a test point again since I did not solve for y. So test, I can use 0, 0 since it's not on the line. 12 times 0 plus 9 times 0 is greater than or equal to 108. 0. So 0 greater than or equal to 108. Well, that's absolutely false. So 0, 0 cannot be shaded this time. That means I must shade above the orange line, away from the 0, 0. To decide how many pies and cakes we should actually really truly make, we need to know what section or sections of this graph got shaded both purple and orange. Well, that was this little triangular region down here. We include the actual lines because they were both solid. So anything that is in this region is actually a real true solution to the system. Okay. I need to be able to tell that you are indicating this is your solution set. Whether that is you make these two very, very light, or you write me draw an arrow and say, hey, this is my solution set, but I need to tell which section you are saying works for both inequalities. Okay, what does the shaded region represent? Well, I guess I just kind of said that, but this time it's in the context of the problem, though. So it's not just in general they work in both problems, but it is a number of pies and cakes that I have, or they, that they have time to bake and will result in the required revenue. So where did I get that answer? Well, the double shaded region always represents the points, the number, or all the points that will work for both inequalities. So I had to ask myself, well, in this context, what does any point, every point on this graph represent? Well, every point, whether you're in the purple, the orange, no shaded region, every point represents a number of pies and a number of cakes. So I said it represents a number of pies and cakes that now work in both. Well, what were the both? What were the inequalities about? One was about time and one was about revenue. So you just take that general answer that it's all the points that work for both and ask yourself, well, what are the points about? Well, pies and cakes. Both what? What were the inequalities about? Time and revenue. Find a combination of pies and cakes that would satisfy all of the constraints. So that's in our dark, our black, double shaded region. So, and we have to show that that combination works. So let's go pick out a point here. Any point in that double shaded region. Well, I can see like 9, 1 would work. So I'm going to go ahead and say, now 9, 1 means 9 pies and 1 cake. Right? We want a combination of pies and cakes, not just two numbers written in parentheses with a comma between them. 9 pies and 1 cake. Now, how do I show that that will work? Well, remember we had a time constraint, which was 2x plus 3y less than or equal to 24. Well, if I substitute 2 times 9, substitute 1 for y, 3 times 1, 18 plus 3 is 21. 21 less than or equal to 24? Yes, it works for time. The revenue constraint was 12x plus 9y greater than or equal to 108. Well, if I sell 9 pies, that's 12 times 9, and I sell 1 cake, that's 9 times 1. That's 108 plus 9, and that equals 117, which is greater than or equal to 108, so this one also is true. So that is how we show that it works. You got to show that you have enough time and you made enough revenue. Find a combination that takes exactly 24 hours and brings in exactly 108. Now, remember, exact it means on the lines. So every point on the purple line is a point that takes exactly 24 hours. And every point on this orangish reddish line is a point that results in exactly $108 in revenue. So if I want both of those to be exact, I need it to be on the orange line and the purple line. Well, that's right here. That's the point where they cross. That's the intersection, which in this case is at the point 6, 4. So 6 pies and 4 cakes. 6 pies and 4 cakes. Show that it works. Okay, so showing that it takes exactly 24 hours, I would do 2 times 6 plus 3 times 4 and show that it equals 24. That's 12 plus 12. And notice I changed this to an equal sign because we wanted exactly 24 hours. And then for revenue, if I sell a pie for $12, that's 12 times 6, and a cake for $9, it's 9 times 4, and I want to show that equals exactly 108. So that's 12 times 6 is 72, plus 36, and 108 is exactly correct there. Number 8, Tommy's certain that he and Kate can make 3 pies and 7 cakes. So that means he wants X to be 3 and Y to be 7 and still meet all the constraints. Do you agree or disagree? Well, you could, I don't think you have to, but you could look back here on your graph first to go to the point 3, 7. Now I can see the point 3, 7 is not in any of the shaded regions. So that would mean it doesn't appear that it's going to work in either time or revenue. Okay. Now, if you are going to decide that you do not agree, right, I disagree with Tommy, then you only have to show that there's one constraint that doesn't work. The fact that both don't work doesn't really pad your argument at all. So if I tried the time constraint with 2 times 3 plus 3 times 7, supposed to be less than or equal to 24. Well, that's 6 plus 21, which is 27. That is not less than or equal to 24. So that right there is enough of a justification that Tommy is wrong. Now, if you went further, or instead, I guess, if you did revenue, that would be $12 for each of those 3 pies, plus $9 for each of those 7 cakes, supposed to be greater than or equal to 108. Well, 36 plus 63 is only 99, and that is not greater than or equal to 108. So, in fact, Tommy, your combination does not meet either of the constraints. So, this combination does not meet either of the constraints. Okay. Now, if you tried time and it did work, that doesn't mean you should agree with Tommy. You still have to check the other one. So if you're going to agree, you have to try it in both. If you're disagreeing, one might be enough. If the first one you try is already a false statement, then you can stop and say, yep, Tommy, you're wrong.